Hello class. This is the first video in a series of lessons primarily dealing with solution stoichiometry. In this lesson sequence, we will also review types of chemical reactions as well as composition of mixtures. In the last lesson sequence, we dealt with principles of stoichiometry. We looked at gram-to-gram conversions, empirical formulas. We looked at percent composition, percent yield, things of that nature. The bulk of the mixtures we're going to see in this lesson sequence are aqueous solutions, meaning they are dissolved in water, therefore in the liquid phase. However, solid mixtures like metal ores and alloys are important to analyze as well. In the 2018 exam, I believe, there's a question dealing with iron ores where you had to essentially do what we're about to do. So it's good to teach. I do like throwing this in here just to make sure we're applying our stoichiometry skills, and then that way we're also familiar with the context of some of these questions that we'll continue to see. So here we have an iron ore that contains primarily Fe2O3 plus other impurities. A 752 gram sample of the impure iron ore is heated with excess carbon, producing 453 grams of pure iron by the following reaction. In this reaction, we have 1 mole of Fe2O3 reacting with 3 moles of carbon, and it is a single replacement reaction, so the carbon displaces the iron. Iron is now free. We produced 2 moles of iron, and the carbon bonds with the oxygen to form 3 moles of carbon monoxide. What is the mass percent of Fe2O3 in the impure iron ore sample? Assume that Fe2O3 is the only source of iron and that the reaction is 100% efficient. So really this is applied stoichiometry and an application of the law of conservation of mass. We can't use this number, the 752 grams, until the very end of the problem because that is the mass of my impure sample. I can't convert grams of impure iron to mole because it wouldn't be an accurate conversion. I don't know what the mass of my impurities are, but I do know the mass of my pure iron. So if I have 453 grams of iron, I can certainly get that to moles. Anytime you're problem solving in a stoichiometry problem, just get grams to moles. That's just the rule of thumb. If you see grams, convert it to moles. You'll probably find something useful from there. So I have the mass of iron is 55.85 grams per mole. And then that is my starting point. This is my A, right? And I want to find grams of B because I need to figure out the mass percent of my iron ore. If I am finding the mass percent, then it must mean I have to get to grams of Fe2O3 somehow. So from my balanced equation, I have 2 moles of Fe for every 1 mole of Fe2O3, and those come from your coefficients, right? So I've got 2 and 1. And then I can convert that back to grams. So with Fe2O3, I've got 55.85 times 2, which is 111.7, plus the mass of oxygen, which is 16 times 3. So my molar mass is 159.7. Now, before I go through and solve this problem, I should do a couple of things. One, I should make sure all my fractions and my dimensional analysis cancel out correctly. Grams of Fe, moles Fe, moles Fe, mole Fe2O3, mole Fe2O3, and I'm left with grams of Fe2O3 for my final answer. The other thing I should do is check my Sig Figs. I see 3 significant figures in my starting amount of 453, so my final answer should also have Sig Figs that match 3 Sig Figs. So 453 Make sure I'm on the right thing here. 453 times the top of the first fraction divided by the bottom of the first fraction times the top of the second fraction divided by the bottom of the second fraction times the top of the third fraction divided by the bottom fraction. Okay, and I get 647.66 and some change. If I'm rounding that, 6, 4, and the 7 stays, but I have to look to the next spot. I have to look to the 6 to see if I round up. 6 would round up, so the 7 rounds up to an 8. 648 grams Fe2O3 is the mass in my original sample. Now, mass percent is what I'm looking for, so I'm not finished. The mass percent is a very similar idea to percent composition and percent yield. Percent yield we know is the actual amount divided by the theoretical amount, whereas percent composition is the percentage by mass of an element within a compound. So percent composition, for example, if you've got one carbon atom, which is about 12 grams, one mole of carbon, which is 12 grams, in CH4, which overall is 16 grams, then the bulk of that mass comes from the carbon. So that has a higher percent composition of carbon than any other element. When we're looking at an ore, or mass percent of an ore, it's a very similar idea, but instead of the percent by mass of an element within a compound, we're doing the percent by mass of compound within an entire sample. So really the process is the same. It's just that the context of how we're solving the problem shifts from elements to compounds. So what that means is if I have my actual amount divided by the mass of my original sample, so 648 was my actual amount, divided by 752, which was my impure sample to begin with, and I multiply that by 100, I get the percentage of purity. So I know exactly how pure my sample is. So 648 divided by 752 times 100, and 86.17% of this sample is Fe2O3. Or you could say it's 86.17% pure, depending on how the question is being asked. The remaining 13 point something percent would be the impurities. So, like I said, it could have some zinc, could have some dissolved gases, a lot of different possibilities after it's been sitting there cooking in the Earth's crust for a long time. Okay, let's go through and do You Try It Set 1. There are 2 problems dealing with iron ores and a 3rd problem dealing with a brass alloy. Okay, welcome back. Moving on to water, the common solvent. So I think for the remainder of this video, we probably will not get to any calculations, and that's okay. We'll just talk about the vocabulary and learn a lot about water. Water is arguably the most important molecule in all of chemistry, and we need to know the ins and outs of it before we can start talking about solutions, which are primarily composed of some solute and water. So properties of water. Water has a high specific heat, a high heat of vaporization, high cohesive and adhesive forces. So some of those things we need to review. The term specific heat is the amount of energy required to raise 1 gram of a sample 1 degree in temperature. So water, we know, if you've ever tried boiling water, it takes a long time and a lot of energy. Water has a high specific heat because of its intermolecular forces, keeping them together. It also has a high heat of vaporization. Heat of vaporization is the energy required to convert all of your water molecules from the liquid phase into the gas phase. So what that means is that energy must be absorbed by water molecules to break the intermolecular attractions between the molecules in order to transition from one phase to the next. Since water has really strong intermolecular forces, it contributes to a higher specific heat and a higher heat of vaporization. And the picture on the right is really important here because you see both the structure of water, you see these little S's, which are really the Greek letter delta, and you see a couple of different labels here and some positive and negative signs. We are going to explain everything that shows up in that diagram momentarily. Before we can start talking about what's going on around the water molecules, we have to talk about what's going on within the water molecules. So the intramolecular forces, aka the covalent bonds, can lend itself to some of the properties that we see as well. So the OH bonds, the covalent OH bonds, are very polar due to a large electronegativity difference and small atomic radii. When we're talking electronegativity, that just means that an atom has a greater ability to pull electrons toward itself. So oxygen, which has a high electronegativity, on the Pauling scale, it's about 3.5, is bonded to hydrogen, which is about 2.1 on the Pauling scale. That electronegativity difference is 1.4. If you subtract 3.5 and 2.1, the difference is 1.4. Typically, a polar covalent bond falls between 0.4 and about 1.8 to 2, depending on which resource you're looking on. So we are on the upper end of our limits of what classifies as a polar bond. Therefore, it's very polar. Since electrons are being pulled towards oxygen, since it's electronegative, the electron density is skewed. This results in a bond dipole. So dipole, if we break apart that word, literally means two ends, so positive end and negative end. And when you are looking at a polar covalent bond, there's a permanent dipole that occurs within the molecule. So I'm going to use an arrow here to represent that. I've got an arrow that points towards the more electronegative element, and then we use a little cross at the end of the tail because it looks like a positive sign. And so you'll see that happen quite a lot. So what I've drawn here in purple are two bond dipoles. They both point the same direction towards oxygen. And the electrons, so imagine you had an electron cloud around your molecule. You would normally think it's going to be some sort of sphere. It would end up looking more oblong shaped or egg shaped because it's skewed to one side of your molecule. So as a result of the electrons being skewed towards oxygen, oxygen ends up with a partial negative charge. And we use delta minus to represent that or to label that. When we're talking a partial charge, that is somewhere between a charge of 0 and 1. It's not a full charge like an ionic compound has, where you have ions like sodium with a 1 plus charge or chlorine with a 1 minus charge. This is somewhere in between. Still enough to cause attraction of opposite charges, but not quite the same to be labeled as an ionic compound. As a result of electrons being pulled towards oxygen, H has a lower electronegativity and therefore is electropositive because electrons are being pulled away from it. Remember, losing electrons makes you have a positive charge. Gaining electrons makes you have a negative charge. So similar idea here. As a result, H ends up with a partial positive charge. The bond dipoles of each OH bond paired with this bent molecular shape that we have here. So remember that a bent molecular shape, you've got two lone pairs on the center atom and two bonds. The bent molecular shape, as a result of having lone pairs on the center atom, lone pairs are more repulsive and therefore push the covalent bonds down in space. And therefore, the water molecule is not straight, it is bent. It's one of the most common issues I see is drawing a Lewis structure for water like this. And while that may get you points for satisfying the octet rule, in terms of shape, that is terrible. Because when you look at your dipoles, they're still pointing towards oxygen, but they're pointing in the same direction. And oftentimes it's misinterpreted as, oh, those cancel out, which they wouldn't anyway, but because a lot of people say water is linear when it's not, it leads to other issues down the line when looking at polarity. So you need to know water is a bent molecule, and as a result of being a bent molecule, it has a net dipole moment. What that means is if I combine the two bond dipoles that I've drawn in purple, overall, the electrons are shifting towards the oxygen side of the molecule. This one I drew in orange would be your net molecular dipole. So your net molecule dipole would look something like that. It goes straight through the center of the atom. Okay. As a result of having a permanent bond dipole and permanent molecular dipole, or a net dipole moment, our water molecule is most definitely polar. Now, because it is polar, we have to talk about the intermolecular attractions it can experience. All atoms, as a quick review, all atoms can experience London dispersion forces. Those are temporary attractions as a result of electron clouds both repelling and attracting each other when they come into close proximity. Those ones don't have much effect on water because water is still relatively small and has few electrons. But the ones that are really important are the dipole forces. So the dipole of one molecule is attracted to the dipole of another molecule. Specifically, in water, we're dealing with hydrogen bonding, which is a special type of dipole-dipole force, and it is stronger than a normal dipole-dipole attraction. It is a terrible name because most students think, oh, it's bonding, therefore it's covalent. No, it is not covalent. Hydrogen bonding is a terrible misnomer, but what you do need to know is it's the strongest type of intermolecular force. As a result of having a strong intermolecular force, the water molecules are going to stick together and require more energy to separate. So we'll talk about that a little bit more in a bit. As a review, a hydrogen bond is when an H is bonded to a nitrogen, an oxygen, or a fluorine. All three of these elements are small and have large electronegativity values. Therefore, the electrons are very skewed towards the non-hydrogen element. It only works with those three atoms. Any other type of dipole-dipole force you'll see is just a normal dipole-dipole force and is not as strong. The partial positive charges in a water molecule can attract partial negative charges of other water molecules. This is what contributes to the ordered crystal structure in ice, and these are referred to as solvent-solvent interactions. So what you see here, again, if I draw those dipoles in, you'll see that the positive ends are attracted to the negative ends and vice versa. And so you'll see that negative attracted to positive, negative attracted to positive, etc., etc. Now, it's called solvent-solvent interactions because the molecules are interacting with each other. If the water molecules interact with something else, like something it is trying to dissolve, we're going to end up with solute-solvent interactions. So these intermolecular attractions also contribute to water being a good solvent. The example I'm going to use here, and we'll see in a bit, is Na plus and Cl minus. We know that salt dissolves in water, and when this occurs, the partial negative that we get for oxygen is going to form an attraction with the positive cation, and likewise, the partial positive H's are going to form attractions with the negative ion. So again, we're applying that idea that opposites attract. And so when water interacts with something it's trying to dissolve, that's referred to as a solute-solvent interaction, as I stated before. Now, there are 3 steps to the dissolving process. I'm going to check my time, and we're going to talk about this dissolving process and then call it a day on this video. So solubility refers to the extent that a solute can be dissolved by a solvent. There are 3 steps in the dissolving process. The first one is overcoming solute-solute attractions. So in that example we just looked at, Na plus is overcoming its attraction for Cl minus. Step 2 is overcoming solvent-solvent attractions, so water overcoming its intermolecular force attractions for itself. And then step 3 is forming solute-solvent attractions, which is the water interacting with the Na plus or the Cl minus, depending on how the process goes. Steps 1 and 2 are endothermic. It requires energy to separate these things. And the third step is exothermic, which means energy is released. The thermodynamic favorability of the dissolving process is dependent on the magnitude of energy necessary for each step. So if more energy is absorbed in steps 1 and 2 than energy released in step 3, the overall dissolution process is endothermic, and you'll see a drop in your temperature. If more energy is released in step 3 than energy absorbed in steps 1 and 2, the overall dissolution process is exothermic, and you'll see an increase in your temperature of your solution. Now, if you have an endothermic process, you can overcome those by stirring the solution and heating it while dissolving. If you add extra energy, you will help things dissolve. Oftentimes when you're making a solution in lab, you'll see that some of the chemicals are a little older and therefore take some more time to dissolve because they've kind of been left out into the open air and they're not as fresh, so to speak. So you need to add heat and stir the solution. When the attractions in step 3 are greater than the attractions in step 1, which are the ion-ion attractions in a crystal lattice, the ionic compound is soluble. So in first year chemistry, we probably lied to you to some extent and just said, oh, everything's soluble, which is not really true. When we get into precipitation reactions, there are certain ionic compounds that are insoluble. And as a result of them being insoluble, they cannot overcome step 1, which is breaking away from the lattice. Doesn't matter how much water you throw in there, it's not going to be quite enough. Usually you need something stronger to help it dissolve. All right, last little comment before we wrap up on this video. Here is a nice diagram of salt dissolving water, as I was talking about before. And orientation matters here when you're drawing particle diagrams like this. I saw it as an FRQ question a few years back. You had to draw water molecules around the ion and they had to be facing the correct way. So you'll see on the anion up here that all the H's, which have a partial positive charge, are facing in towards the negative. And then when you look at the positive, all the oxygens, which have a partial negative charge, are facing in towards the positive. It does matter because of the opposites attracting principle. Okay. In our next lesson, we'll talk about dissolving polar and nonpolar substances and the nature of strong and weak electrolytes. That is all for today.